We are currently moving into the last unit of our organic section, and any units after this, as we move down the road, will be primarily biochemistry. Again, the two are very related, but you will notice some differences as far as the approach of looking at the different types of structures in the biochemistry realm as opposed to the organic realm. So in this unit, we're going to be looking at our last couple of functional groups, amines and amides. They are the ones that are nitrogen containing. Here's a general structure of an amine and a general structure of an amide. We'll go into more detail later about what these R groups are, but for now we can say that whether it's an amine or an amide, these R groups are either a hydrocarbon type carbon or a hydrogen. We will start looking at amines. Again, of these nitrogen-containing functional groups, if we have a nitrogen atom, which, as we see here, obeys the standard bonding model, 3 bonds emanating from it, 1 lone electron pair. If those 3 bonds all terminate in either a hydrogen or a hydrocarbon type carbon, then it is an amine structure. So the nitrogen component is usually considered an amino group. This amino group, just like the OH on an alcohol is considered the hydroxyl group. This is a little closer to the actual name of the functional group. It is the amino group. Now, notice on some of these representative structures that just like the hydroxyl in an alcohol, sometimes we can approach these with condensed structure. If we look at the structure, for instance, over on the left, notice there are still 3 bonds emanating from that nitrogen. It's just the 2 of them, specifically connected to the hydrogens, are condensed rather than 2 covalent bonds emanating from that nitrogen terminating in a hydrogen atom. We just write NH2, and those covalent bonds are assumed. We'll be seeing this a lot with nitrogen-containing functional groups, amines and amides, very much like we contract the hydroxyl on an alcohol or the hydroxyl portion of a carboxylic acid. But in these 3 types of structures, there are 3 representative amines. All of the 3 bonds emanating from the amino group, in each case, terminate in either hydrocarbon type carbon or hydrogen. So one thing that is important about amines, which we'll be looking into, is that amines have a weakly basic character. Basic meaning the opposite of acidic. So they act as weak bases due to the very active lone electron pair, which is always on that nitrogen atom. We'll be looking at that in a little bit more detail when we start talking about reactions of amines. But just understand that amines are slightly basic. We've already seen another functional group which was acidic. That was the carboxylic acid in the last lecture. But amines are considered to be basic, weakly basic. Now, if you remember our idea of classification, we classified alcohols, we classified various carbons and various alkyl groups. When we hear the term classification in organic chemistry, that means that we're going to be looking at 3 possibilities in this case. Primary, secondary, or tertiary, or if you can use those phonetically, or use these very abbreviatory ways of expressing primary, secondary, or tertiary. For these nitrogen-containing functional groups, it is very easy to determine a classification, and all it is counting the number of carbon atoms attached to the nitrogen. That's it. So if we look at, for instance, the amine over on the left, how many carbon atoms are attached directly to that nitrogen atom? Well, there's only 1. The other 2 bonds of that nitrogen terminate in hydrogen atoms, and it's given as that contracted expression. But since there's 1, it is a primary amine. the amine in the middle, well, we have ending up with two carbon atoms directly attached to it. So this would be an example of a secondary amine. And lastly, the third one, we have 1, 2, 3 carbons directly attached to that nitrogen. So this would be an example of a tertiary amine. Now, holding these the examples of primary, secondary, and tertiary amines up top, we have another ability of amines. Remember, hydrogen bonding is possible in molecules containing either OH bonds or NH bonds. Remember that NH bonds also allow for hydrogen bonding. So if we look at the this markup here of a representative primary, secondary, or tertiary amine, we can say that in the primary amine and in the secondary amine there are NH bonds. We can see that, NH. However, tertiary amines have no NH. So therefore, all amines are not considered equal with respect to intermolecular forces. Only primary amines and secondary amines bear hydrogen bonding. So if we had a comparison of three amines of identical or similar molar mass, indeed these are identical molar masses down on the bottom because they're constitutional isomers, and we put these together as a representative primary amine over on the left, secondary amine on the right, and tertiary amine way over on the right, we can look at their representative boiling points. The first two, the primary amine and the secondary amine, have hydrogen bonding, different amounts, but clearly these boiling points are well up into the 2 digits. We have about 50 degrees and about 35 degrees respectively. Take away that ability to hydrogen bond, however, and we look over at the similarly massed tertiary amine, well, we're almost at a 0 degrees Celsius boiling point, a dramatic drop from what we saw in the first two cases. So all amines are not considered equal with respect to hydrogen bonding. We got to have NHs in order to hydrogen bond. And onward we go into nomenclature. IUPAC amine nomenclature. This will be the last unit of study where we're looking at IUPAC nomenclature. When we get into the biochemistry section, we'll be talking about names of various carbohydrates or lipids or that sort of thing. But this is the last unit where we'll actually be going through this rule-based nomenclature. So as always, in these IUPAC nomenclatures, we have to first identify the longest continuous carbon chain containing the amino group. And we want to be cautious here because we could say, it's tempting to say, all right, I'm going to count throughout. We have 1, 2, 3, 4, 5, 6, 7, 8. It's very tempting to do that. But we have to be cognizant that this has to be the longest continuous carbon chain. Continuous. Notice what I did up top. That's not continuous. We have a nitrogen right there that breaks the continuity. So that's not a continuous carbon chain. So thus, we have to look to either side of the nitrogen, and in this case, and say, well, how many carbons do we have? The one with the most carbons wins. Well, here's 1, 2 carbons, and here's 1, 2, 3, 4, 5 carbons. It is that 5 carbon units that is the longest continuous carbon chain. So that is my parent structure. So what we have here is a 5 carbon chain. If this were a 5 carbon alkane, it would be known as pentane, but it's not. Again, it is an amine. So in true IUPAC fashion, now we remove the E from the corresponding alkane name and replace it with a different suffix. That suffix is amine. Pentane becomes pentanamine. Pentanamine. Fair enough. Now we have to number that parent chain, giving the carbon containing the amino group the lowest number. This might seem counterintuitive, but remember, if we look up top at that red portion where I've highlighted the parent chain, I could have, for instance, a the amine not connected to that end carbon, but perhaps it could be connected to an internal carbon. We'll be looking at some examples of that on the next pages, but it does matter. So we have to number this parent chain. We would number from, in this case, right to left, in order to give that amino group an attachment at the lowest numerical designation, that 1 carbon. After we do that, we have to prefix that pentanamine parent name with the carbon number which that amino group is attached to. Look, that nitrogen is connected to the 1 carbon. So we'll put 1 pentanamine. And now we enter into something wherein we're really in different territory now. We typically will put in these substituents on a parent structure. There aren't any here, but if we had a chloro at the 3 carbon or a methyl at the 4 carbon or whatever, but we have a different possibility for alkyl substituent now on these nitrogen containing compounds. And indeed, we have something connected to the nitrogen. All of the carbons in that molecule have not been accounted for. Just those 5 in the parent structure, right? We still have a couple of carbons left. They are not connected to the parent structure, those 2 carbons right there. They're connected to the nitrogen. So thus, we identify that group, and that is an ethyl group. It's a 2-carbon ethyl group, but it, instead of connected to the parent structure, is connected to the nitrogen. So instead of 2, 3, or 4 ethyl, or that sort of thing, 1 pentanamine, we write N-ethyl 1 pentanamine. N-ethyl because that ethyl group is covalently bound to the nitrogen, not the parent structure. We're going to be seeing this a lot as we move forward, especially on the next slide when we look at some examples. So some more complex examples of IUPAC amine nomenclature. We can start with the structure over on the left. And the first thing we do, as always, is look for that longest continuous, remember, continuous carbon chain. That would be the one that I'm outlining in red here. Remember, so that's a 7-carbon chain. These carbons up here continuously are only 3, and we always go with the one with the most carbons as the parent structure. So if this were a 7-carbon alkane, it would be heptane, but it's not. We recognize this as an amine, so we are going to name it as such. We remove the E from the corresponding alkane name and bring in the suffix amine. Heptane becomes heptanamine. Now we number this parent structure from the side which brings the amino group at the lowest numerical designation. I hope you can see that that amino group is squished over to the right on that parent structure somewhat. So we would start numbering from the right to bring in that amino group covalently attached to the 3 carbon. And thus, we will prefix that heptanamine with the number 3. 3-heptanamine. Lastly, we have this 3-carbon structure up here that has not been accounted for yet, and it is attached to the nitrogen, the amino nitrogen. So that 3-carbon structure is a propyl group attached to the nitrogen, brings us in for N-propyl 3-heptanamine. Final answer. The second example in the center here, longest continuous carbon chain, well, we have to meander a little bit around, and it turns out to be these 9 carbons that we see right here. If this were a 9-carbon alkane, it would be nonane, but it's not. We recognize this as an amine, so we're going to name it as such. We remove the E from the corresponding alkane name and bring in the suffix amine. Nonane becomes nonanamine, right? Now we have to number the parent structure such that the amino group comes in at the lowest numerical designation. Well, this is actually an example wherein it doesn't matter which way we number on this naked 9-carbon parent chain. we would still bring in the amino group at the 5 position. So, I mean, you could try it both ways. I'll show it one way. We always bring in, if we numbered it in the other direction, it would still bring in that amino group at the 5 position. So it doesn't matter in this case. So we are going to prefix that nonanamine with the number 5 because that's where the amino group is. Well, we still have two carbons that are unaccounted for, two single carbons, and both of these are methyl groups. Both are methyl groups. So this would be a dimethyl, both connected to the nitrogen. So watch what I do here. We have to say N twice. N, comma, N dash, dimethyl 5-nonanamine. It's a little counterintuitive, not one N, but two. NN dimethyl 5-nonanamine. And the last one over on the right, going from name to structure this time. N-ethyl, N-propyl, 2-butanamine. A lot to unpack there. Well, let's look at the very end. I see butane right there, or butan, if you will. But means 4, and that's the parent structure. So here is 4 carbons in a line, and I'm going to number these in any direction I want to. I'll start left to right. And we notice that it is an amine, so there's going to be a nitrogen attached to what? The 2 carbon right over there. So I'm going to put a nitrogen attached to the 2 carbon, and then I'm going to bring in some N substituents here. There's an ethyl group on the nitrogen, which I write in here, and also a propyl group on that nitrogen, which I put in as shown here. So in this case, we have N-ethyl, N-propyl, 2-butanamine written in the proper fashion. So finally, we've made it over to reactions of amines, or reactions involving amines. And since amines can act as bases, they're weakly basic, we can undergo an acid-base reaction with them. The very active lone pair on the nitrogen atom on the amine over on the left, when put in the vicinity of a strong acid, will remove the hydrogen ion from that strong acid. What we ultimately end up getting, if we could follow this, is that lone pair on the nitrogen then becomes a covalent bond connected to that abstracted hydrogen, the one that was taken off. And since it's picking up an H+, that neutral amine then becomes positively charged. And we balance that positive charge with the chloride ion, which is produced once the chlorine from the strong acid takes possession of both of those electrons that were in that covalent bond. So what we have here is another type of salt. Specifically, it's known in a general sense as an alkyl ammonium salt. Alkyl ammonium salt. Well, that's because this is an alkyl group, R1. It's a hydrocarbon type carbon. And when you have an NH3+ on there, it's considered an ammonium ion. So an alkyl ammonium salt, because we're recruiting in that counter ion chloride as well. So the reaction of an amine with a strong acid produces an alkyl ammonium salt. So this fits very nicely into what's in the box plan. If we look at a couple of examples here, we have an amine on top with a strong acid, HBr. And we should be able, that's supposed to, that's a spontaneous reaction, and we're being asked what that gives. Well, we would have to put 2 and 2 together here and say, like, we have our amine plus a strong acid. We are going to make that alkyl ammonium salt. And so how does that look different than the amine itself? Well, ultimately, we remove that hydrogen, and that's going to become a covalent bond then with 2 hydrogens ultimately attached and a positive charge at the nitrogen, ultimately, is what we're going to be seeing with the counter ion bromine or bromide given as shown here. So most of that original amine is still there. We've just added a bond hydrogen and a positive charge on the nitrogen, of course, recruiting in that Br minus bromide ion as the counter ion. Looking at the example on the bottom, we've switched it around a little bit. We have our what's in the box as a starting material. Something plus HCl gives this alkyl ammonium salt. So what do we have here? Well, that's going to be an amine in that starting material box, but we're ultimately have to deconstruct this backwards. What did that amine look like from this alkyl ammonium salt? Well, we were going to take away the positive charge on that nitrogen and take away that bond hydrogen, ultimately. So what is that going to give? Well, what we see right over there, that tertiary amine starts us out. That tertiary amine plus HCl gives what we see in the product profile there. So let's move over now into our second nitrogen-containing functional group, that of amides. Now, an amide is different than an amine, and sometimes that difference is subtle. Typically, it is a functional group with nitrogen in it, looking over here on the right-hand side, but different than amines, that nitrogen is always connected to a carbonyl carbon. That's not a hydrocarbon type carbon. It is a carbonyl carbon. A hydrocarbon type carbon is a carbon directly attached to only other carbons and other hydrogens. A carbonyl carbon is also attached to oxygen, and thus it makes it different. So an amide can always be recognized because it is adjacent to the carbon of a carbonyl in this case. So that is the difference in structure between amides and amines. So here are some representative amides. I've drawn them to be somewhat similar in structure to our representative amines, perhaps, that we looked at before, but these are definitely amides. In each case, the nitrogen atom is directly adjacent to a carbonyl carbon. That was different than any other amine that we have looked at. As with amines, these hydrogens, if they're on there, can be written in a sort of condensed fashion if you want to, or if you wanted, you could put a covalent bond connected to a hydrogen atom with each of them. Either way is fine. As we move forward, we'll be able to see the similarities of these amides with amines as well as their differences. Now, an amide is essentially, and we're going to see this, a fusion between a carboxylic acid and an amine functional group. Remember, our ester was a fusion between a carboxylic acid and an alcohol functional group. Now we have an amide is the result of a functional group condensation, which we'll see before. We have our carboxylic acid portion of our amide over on the left-hand side and the amine portion over on the right-hand side as it is drawn here. So let's look at a striking difference between amides and amines. Now, whereas amines are basic, and they're basic, they act as bases because they have a very active lone electron pair which can reach out and capture a hydrogen ion. If we had a strong acid strolling by, we could, that lone pair is always right there and very willing to reach out and grab that hydrogen off to become that aforementioned alkyl ammonium salt that we talked about before. But amides are built a little differently. Yes, there's still the lone pair on a nitrogen always, but in amides, the activity of that lone electron pair is attenuated somewhat. So here's a representative amide structure, a very general amide structure, and that lone electron pair that we see on the nitrogen is not just waiting always on that nitrogen for a nice juicy strong acid to go by. it actually sort of plays hot potato with itself and can give this sort of, it can throw those two electrons of the lone electron pair towards the carbon of the carbonyl, and those two electrons on that carbon-oxygen bond can go and live up by oxygen. It can do this. In fact, it does do this. So we get this really weird structure we see here over on the right, but then we can collapse that electron structure again and move back to the original one. This is yet another example of a resonance hybrid. Do you remember back when we were looking at aromatic hydrocarbons? We had in the aromatic ring, the 6-membered ring with alternating double and single bonds. We had those double bonds being able to sort of zip around that ring. They were considered delocalized. Well, the same idea works with amides. We're sort of going back and forth between one structure and another, so that the actual structure of the amide doesn't look like this, and it doesn't look like that. It's somewhere in the middle, which is why they call it a hybrid. In fact, it sort of defies the ability to draw it correctly because it's sort of halfway between those two forms. That's why we put this resonance double arrow in here to show that, well, it's a hybrid. We're somewhere in between those two forms. Having said that, it really makes a statement as to the activity of this lone electron pair. That lone electron pair is not always there on that nitrogen. If we look over here, we don't, on this nitrogen of this resonance contributor, we don't have a lone pair. So it's just kind of halfway there. If, that's not a real scientific way of saying it, but it's not all there, to be colloquial about it. So it's not all that available for when a strong acid should come by for being able to reach out and abstract a hydrogen ion from that strong acid. In fact, if you put a strong acid in the vicinity of an amide, that lone electron pair won't do anything because it's too busy going back and forth between the nitrogen and up into the oxygen of what once was that carbonyl. We can also classify amides, remember, just like we did with amines. And with amides, we are able to carry this out, this classification, just as easily with amines. Remember, classification is either primary, secondary, or tertiary in these cases. So that just like with our amines, if we literally count the number of carbons that are directly covalently bonded to the nitrogen, this time in amides, that will be the classification of the amide. If we look at the structure over on the left-hand side, well, how many carbons are directly attached to the nitrogen? Just one. So this would be an example of a primary amide. The one in the middle, there are 2 carbons directly connected to that nitrogen, so this would be a secondary amide. And lastly, on the third one, over on the right, we have 3 carbons directly attached to that nitrogen, so this would be a tertiary amide. Now, as with amines, while we get a difference in the intermolecular forces between them depending on what form they're in, we find that primary and secondary amides have NH bonds right there. But tertiary amides do not have NH bonds on them. Remember, NH bonds are hydrogen bonders, the strongest intermolecular force. So if you have NH bonds, you're probably going to have stronger forces holding those particles together than if you did not have NH bonds on the molecule. So thus, we can really do a good boiling point comparison now of amides, depending on whether they have with them NHs on their structure, in the cases of primary and secondary amides, or no NHs in the cases of a tertiary amide. Here I have three amides put together. They are constitutional isomers of one another, so they have identical molar masses. Let's try and deconstruct these a little bit and get a better understanding. So we know our primary and secondary amides, the one on the left and the middle one, have hydrogen bonding ability because they have NHs, whereas the tertiary one has no H bonding ability. So look at these boiling points now. The primary and secondary amides have boiling points of around about almost exactly the same, about 220 degrees Celsius. Whereas look over on the right, the boiling point of the tertiary amide is significantly lower. They're all high boiling points, but it's significantly lower. This is a comparison, and that is because that tertiary amide does not have hydrogen bonding ability like our primary and secondary amides. Okay, so this is the last time in this course you will be subjected to IUPAC nomenclature. Finally, we're at that last functional group. Not everything after this is biochemistry, and there's no IUPAC in biochemistry. So IUPAC amide nomenclature. IUPAC is, as we know, has very similarities between most functional groups. What's the first thing we do in IUPAC is to find the longest continuous carbon chain, in this case, containing that amide carbonyl group, that carbonyl carbon right up top here. That is important because we are going to count that carbonyl group when we look at our structure. So what is the longest continuous carbon chain containing that amide carbonyl is this one right here, these 5 carbons. And if this was a 5-carbon alkane, it would be pentane, but it's not. We would analyze this and recognize this as an amide structure, a nitrogen adjacent to a carbonyl carbon. So we remove the E from the corresponding alkane name, pentane, and replace it now with the suffix amide. Pentane becomes pentanamide. Now, just like aldehydes and just like carboxylic acids, that carbonyl group is always on an end. So that there's no need to number this amide parent chain. I'm not going to be bringing in, at least for this course, for you, any substitutions on the parent chain. So it'll just be a naked parent chain. So we don't have to number it because it's always considered that one carbon. That carbonyl always sits on that one carbon. So we're not going to bother with numbering with amides, my gift to you. The other thing, just like amines now, we can have the potential for N substitution. N substitution, remember that. So we have another carbon on here that is not accounted for. And that, so we have to deal with these N-alkyl terms. This is a secondary amide, and we look at that carbon and we recognize it as a methyl group, a 1-carbon methyl group. So we're going to finish this off with N-methyl pentanamide. N-methyl pentanamide. Let's look at some examples of IUPAC amide nomenclature. Looking at the structure over here on the left, we recognize it as an amide, and we look for that longest continuous carbon chain, which includes that amide carbonyl. That would be these 10 carbons right here. If this were a 10-carbon alkane, we would call it decane. But it's not. We recognize that already as an amide, so we remove the E from the corresponding alkane name and bring in the suffix amide. Now, since I told you that I'm never going to be, at least for this course, putting substitutions on the parent chain, and number 2, we see no N substitutions on that nitrogen. There are no alkyl substitutions on there. All of the carbons in this amide have been accounted for. So this is indeed the name, just decanamide. We don't have to put anything else in there. We don't have to say it's 1 decanamide because it's always 1. We don't bring in lasso any N-alkyl names because that is a naked nitrogen. There are no methyls or ethyls or anything on there. So decanamide is the name in this case. Let's look at the second one. Longest continuous carbon chain, including that carbonyl, would be the 6 carbons we see here. If this were a 6-carbon alkane, we would have hexane, but we do not. We have an amide in front of us. So we remove the corresponding alkane name E and put on the suffix amide. Hexanamide. Now, we have some carbons that are not accounted for. We over connected now again to the nitrogen. We have a methyl group and a propyl group. 1 carbon and 3 carbons respectively. When we have something like this, now we have to mention them. They're both N alkylations connected to N, but we have to bring them in alphabetically. M in methyl comes before P in propyl, so we come out with the following. N-methyl, then N-propyl hexanamide. N-methyl, N-propyl hexanamide. Looking at the name over on the right-hand side, we have to build a structure, and as always, we go to the very end. How many carbons in the parent structure? Well, I see ethane right there. Eth is 2. In line drawing, that's just this short line right here, where there's a carbon at each of those ends. However, we see that this is also an amide. So I am going to, on those 2 carbons, looks kind of strange written in line drawing, I am going to put an amide nucleus, just like that, because one of those 2 carbons on that 2-carbon parent chain is that carbonyl carbon. Fair enough. And now I look over to the front. N, comma, N, diethyl. So we have 2 ethyl groups, each connected to the nitrogen. And we would just draw them on there, 2 ethyl groups. So this would be the finished structure of N,N-diethyl ethanamide. And lastly, reactions involving amides. This reaction will be the preparation of amides through a functional group condensation of, as we said before, a carboxylic acid and an amine. If we put a carboxylic acid and an amine together, as we see here over on the left, it will form an amide. However, only under very forcing conditions of very high heat and high pressure. This can make this a dangerous undertaking. If we want to make an amide, we have to have very high heat and high pressure. And ultimately, what gets spit out of here is also water, which we see way over on the right-hand side. H2O. Where does that come from? Well, we take one, look over on the left, we take one of the hydrogens from our amine and OH from the carboxylic acid, and everything else we connect together into that amide form. So, but again, high heat and high pressure will give you an amide from a carboxylic acid and an amine, but that's dangerous. It can require specialized equipment you may not have in the laboratory. So what we can do is to recruit a carboxylic acid derivative, a much more reactive one, to react with that amine, and we can use it to spontaneously now produce an amide. So here it is, a much easier way of making an amide using that carboxylic acid derivative, a very activated one, if you will. Do you remember that acid chloride that we looked at, that weird one, which had a chloro group attached directly to the carbonyl carbon of that, what once was a carboxylic acid? That seemed really strange, and that was one of our reactive intermediates in organic synthesis. We can recruit this in this case because what's going to happen is if instead of using or reacting together a carboxylic acid and an amine, I will react that amine with the much activated carboxylic acid derivative, the acid chloride. And I'm going to find that we spontaneously now produce our amide plus hydrochloric acid as a side product. Spontaneous reaction to form the amide is much more preferable than having those dangerous conditions of high heat, high pressure, specialty equipment perhaps being needed. This now we see there's nothing over the arrow, so that means this reaction proceeds spontaneously, and that's great. Now we have the ability to get into an amide structure without having to employ dangerous conditions. So let's look at some what's in the box questions here in the preparation of amides. And again, when we play what's in the box, we're being detectives, we're being sleuths and trying to figure out what should be in the box given the information we have. If we look at the example up top, we have this sort of strange looking, but it is an acid chloride, and this strange looking, but it's still an amine. An acid chloride and an amine gives something plus HCl. So with all of that information, we should be able to say, oh, this is going to be an amide-forming reaction of an acid chloride and an amide. So ultimately, we would have to make an amide sort of undercurrent or an amide framework and just tack in the particular architecture we see on the carboxylic acid side as well as on the amine side, and we would give a structure shown here. We would have to, but by definition, by architectural definition, this is the amide that we would have to produce. Looking at the bottom one here, we have in both cases, we have, notice they're labeled here, an acid chloride and an amine. Okay, well that's a dead giveaway because clearly we have an amide here and we're spitting out HCl as a side product, so we just have to be able to draw the acid chloride and what amine we're going to be getting. And to do that, we look right back at the original one. What is the architecture that's going to be on the acid chloride? Well, these two carbons right here. What is the architecture that's going to be on that amine? Well, this isopropyl type structure that we see here. And indeed, we're going to be looking at exactly these architectural motifs onto an acid chloride and an amine structure.